Hi guys, this is AK and welcome to your third periodic table tutorial. Me and my partner are tired. It's 5 a.m. and please excuse me if there is a certain mistake in my tutorial. I will put a caption in the end to rectify my mistake. Alright, anyway, let's get on to the third. No, wait, we won't finish with the ionization potential. So guys, we learned in the previous tutorial that as we go from left to right across a period, the ionization potential increases due to the decrease in the atomic size. So guys, I'm not going to be going over it again. I'm going to come to the next topic under ionization potential, which is a variation of ionization potential in a group. Now, guys, we've been through this before in the second tutorial that in a group the atomic size increases as we go from top to bottom. So, guys, if you look at the first group, which is hydrogen, lithium, sodium, potassium, rubidium, cesium. Don't worry, even you guys will be able to. I'm so sorry. You even you guys will be able to learn all this by the end of the year. And in case you are watching this tutorial at the end of the year, you should be familiar with these elements. And francium. Because another thing, francium is radioactive, so I'm still going to consider it in my example. Alright guys, so this is the first group, and as we go down, we know that the atomic size increases. So if I take hydrogen, this is nucleus, and this is the first shell of hydrogen atom, and this is the only electron. And now if I take if I take francium now, so this was hydrogen and this is francium. Now I'm not going to be drawing all the shells, but this is the nucleus, and let this be the last shell, or as we know it as valence. Oopsie. Oh, you guys are really tired. Valence shell. Right. Now another thing, I do know one thing for sure, that even francium in its valence shell will have only one electron, since it lies in group 1. Now guys, if you see the group number indicates the number of electrons in the valence shell. So in case we're talking about group number 17, it will have 7 electrons in its valence shell. Although it is 17 guys, we also take it as 7a, but according to the new convention, group 7 is also known as group 17. I mean, pardon me, group 7a is also known as group 17. Anyway, I'll be going over that later in the bonus periodic table tutorial. So now guys, as I was talking about the ionization potential as we go down a group. So guys, if you see that francium will have a larger atomic radius than hydrogen, and so the nucleus in francium will have a lesser hold on the valence electron, or the last electron, vis-a-vis the nucleus in hydrogen having the hold on the last electron in the valence shell of hydrogen atom. So guys, tell me, don't you think it'll be easier for this electron to get out of this atom, of this shell, in comparison with this electron here in the valence shell of hydrogen, because of the larger radius here? Yeah, guys, you're right. If the radius is large, then the force of attraction between the nucleus and the electron, as I already told you, will be less. And so the energy that will be supplied to break this bond would be quite less than the energy that you need here to supply to this electron in order to get it out. So guys, as we can see, francium here will have sorry guys, so francium will have the least ionization energy. Now, in other words, I can say that it'll be easiest for the last electron to be ejected out of the valence shell in francium. So the energy needed to get this electron in francium out will be the least in this group, guys. So now we're almost done with ionization potential. Just to recap, in a period from left to right, ionization potential increases due to the increase in nuclear charge, or sorry, the effective nuclear charge between the electron and the nucleus. And in a group, guys, from top to bottom, the ionization potential decreases due to the number of shells being added and the effective nuclear charge between the nucleus and the last electron decreasing. So guys, as you can see, this is really simple. You just need to get your concepts right. uh, Now I'm going to be going on, since we have to rush onto the next physical property, which is again pretty easy topic, but this is also the trickiest subtopic under this periodicity of physical properties of elements. Alright guys, now guys, we will be going over through electron affinity. Okay, so as we've already discussed about ionization potential, guys, that it is the amount of energy absorbed to remove one or more electrons from the valence shell of an isolated gaseous atom. uh, Electron affinity is more or less the opposite thing. So guys, in electron affinity, energy is released from the atom in order to add one or more electrons to the valence shell of an atom. Okay, so let me explain this to you using an example. Let's take the example of sodium first. I love these elements. So we've got Na, got the nucleus, this is the first shell, second shell, and third shell. And on the other hand, I have chlorine. I told you I love these elements. 1, 2, and 3. There you go. Cl, guys. Right. Uh, Let me draw the electrons. This time the electrons are crosses, guys, so don't get confused. And this will be the valence electron, since sodium has an electronic configuration of 281 and chlorine will have an electron configuration of 287. And my partner's telling me to change the color, so I will change the color. Here you go, current. Oops.
Thanks.
Welcome, bro. 2, 1, 2. I hit. Right. And similarly, there will be 7 here. 3, 4, 5, 6, 7. Now guys, as we're discussing about electron affinity, or again electron enthalpy, whichever way you want to call it, which one do you think would want to gain an electron and acquire a stable configuration? Now, if you're thinking that it's chlorine, then I should tell you that you're thinking the right way, because indeed it has just one electron in deficit, and if it gains that electron, it becomes 2, 8, 8. This way, it completes its law of octet. Now, we already covered this in the chapter on chemical bonding, in case you don't really know what this means. this is basically a law of chemical bonding to gain stability in atoms. Uh, atoms basically want to the unstable atoms basically want to attain stability, and they can only do it by two means: by fulfilling the law of duplet or law of octet. In this law of octet, if they have 8 electrons in the valence shell, then we consider it to be a stable configuration. And if at all sodium does acquire an electron, it gains an electron and its configuration just adds up to a 2 here, which would require enormous amounts of energy, because this way it is not really stable, and it would like to become stable by only using little amount of energy to remove this electron, guys, and not add another electron. So this way electron affinity is quite the opposite of ionization energy. So guys, we can conclude that in order to add an electron to sodium, you need loads of energy, and that enormous amount of energy is known as electron affinity. Now guys, alright, so what we conclude right now from here is that in a period, if sodium is here and chlorine is here, then electron affinity for this is quite low. I know that electron affinity is the amount of energy that's released in order to add another electron. However, and that energy for sodium is very high. However, still sodium possesses a very low electron affinity in comparison with chlorine. Now guys, you might have this question, and a lot of times this is a really tricky portion. Just please hear me out. But the only reason behind this is that when you're traversing from left to right in a period, please remember that in this case, energy is released and not absorbed. And throughout the world, it's taken as convention that whatever is released is taken as negative, guys. So, guys, if I take an example this way, that sodium has an electron affinity of minus 13.7 electron volt. Now, electron volt is another unit. I will be telling you the conversion between electron volt and joule later. But please remember, guys, you need to add this negative, and even if this is not added, then it's in case of electron affinity, this much amount of energy is released, guys. So please tell me that if after chlorine, argon will have a 0 electron affinity, and if you move in from left to right and I say that electron affinity is increasing, then to finally reach 0 out here, don't you think the number next to argon, next to 0, would be something close to minus 1, maybe 0.2? So guys, now this way your energy is increasing. And so guys, if the amount of energy is increasing, then the electron affinity will also increase. So guys, this is not as easy as ionization enthalpy or potential ionization potential. Please guys, please do remember that in electron affinity you have to get the negative sign. And if you're using Anita Prasad, this is not given. The only three things given are that if the atom is small, then electron affinity is high, and if electron affinity increases with an increasing nuclear charge, and also electron affinity of elements having completely filled orbitals or less than half filled orbitals is practically 0. All these three rules are absolutely correct, but in order to gain clarity, please guys, please understand this negative convention. If you still have doubts, you feel free to contact us. We will give you the address later, but try and understand this in the tutorial itself. In this segment, I've already explained to you, sorry, these first two rules, and the third rule being electron affinity of elements having completely filled orbitals or less than half filled orbitals is practically 0. So guys, as I've already read out the third rule, uh, just imagine that you don't even need to imagine, just take the example of sodium, magnesium, aluminium, and silicon, phosphorus, sulfur, chlorine. Just take chlorine and argon. So guys, This would be a complete octet or completely filled uh, orbitals, and these three people would be less than half filled orbitals. Don't get confused with this word. It's it's really important in your senior classes, but as of now, just take it as less than half filled shells. All right. So guys, now this will have a configuration of 281, similarly 282, and similarly 283. Now, if you can see, then these three would like to lose these two, one, two, or three electrons and gain stability instead of gaining five, six, or seven electrons. So, guys, this is the only thing that that was missing here, and I think I've covered this. Now, I do think that in order to cover certain other portions before the bonus periodic class, I will be using another tutorial. So I'm sorry, this is not going to be your last periodic table tutorial. I hope you've understood whatever I've just taught you well, but still there are certain things that remain uncovered, which I will cover at the beginning of the next tutorial. Keep watching, guys. This is AK signing off.